of this very nice and interesting HPC workshop. So we start our session on performance. So we have different talks about performance of models and different tools also, and also some more general talks about CMCC consumption, including the energy needed to run our simulation and the carbon produced. So we start with Mario Acosta, who will talk about CPMIP performance metric for CMCC, lessons, recommendation, and next steps. So please, Mario.
Thank you, Sophie. Okay, so yeah, this is one particular activity that we were talking in IS-ENES3 project. There is a lot of people involved. Actually, yesterday we saw a table coming from these results. I'm going to talk briefly about the result, but in this particular case, I would like to talk more about the lesson from the collection, recommendation, and the future about this. As a brief introduction again, well, we know from the weather and climate modeling that the typical computational metrics, as I know, for example, the typical impact test and the teraflops per second, these kind of things are not totally useful for our kind of models. Some years ago, Balaji et al. Developed a set of metrics which correspond a little bit more with the representation of computationally of our models. And on the other hand, we have this CMCC, no? This coordinated experiment that at the end provided us a unique opportunity to exploit this set of metrics, no? Performing for first time this complete computational energy analysis and the creation of a novel database on this CMCC experiment. At the end, we have a complete database for different models and platforms and the evaluation of these kind of results. All this work were presented in a IS-ENES3 deliverable with these three particular points. In this case, I would like to talk more. I will focus in the first one. No, I will briefly talk about the first two, and the most important, I think, for this particular workshop is the third one for discussion. I'm not going to explain really all these metrics. This is the CPMIP metrics, no, evaluated also for CMCC. So you have a paper, also the deliverable, and only please take into account this particular, no, that they are going to be useful for the presentation. So the actual simulation just per day, which at the end is how affect your simulation just per day, the queue time, interruption, so at the end is comparing the time stamp from the beginning to the end of the experiment, parallelization, the number of parallel resources that you are using, the joules per year simulated, this is obviously how much energy is used for the specific simulation, and finally the coupling cost, which is how much time and resources I use for the coupling algorithm itself, and also the possible load imbalance of the coupled model. No? In this case, we are talking about coupled model. As I said at the beginning, a lot of people involved from different model institutions. So one bullet here, we are including 11 models with 32 CMCC configuration for this particular study. So for the first one, some possibilities and collaboration with other groups. Something important to say that all these numbers are available in the ES-Doc and the rest of the CMCC experiment, so we are not talking about an Excel with the results. And also we have some discussion to improve actually in the future this update of the performance metrics, for example, including some metrics per component. Also we did some collaboration with Jean-Claude and the HPC Task Force. I'm not going to talk about this total number because actually Jean-Claude is going to do a presentation later. The single point that we can use this kind of numbers to produce another kind of results and analysis. And actually, for example, for this carbon footprint, that there is another group in the IS-ENES3. For example, we can try to calculate this total energy cost for all our experiment, and also a first approximation, calculate this total carbon footprint. So I'm not going to enter in detail. There is some explanation about how this is calculated, and we can discuss if needed. So the only thing to highlight here is the one conclusion. No, this coordinated collection is not only a dissemination and computational analysis actually. So we are creating a complete database that we can use for different activities. No, for example, this paper that Jean-Claude is working now. For example, this invited talk that I did for the WBCRP workshop, talking about the carbon footprint for our model and also as institution, as BSc. So for the second one, usually I spend all my time in the result, in the analysis. In this case, only a brief summary. So for the deliverable, we were talking about these first 5 points, no? Discussing with the multimodal, for example, no, the complexity impact for the different models. Also in a previous work, I did a similar work, but only for ECR. So in this case, instead of the multi-model comparison, we take one model and compare different platforms, compare different configuration, and also is there. In this particular case, only I'm going to remind a little bit about this specific 2 point with the actual simulation just per day and the coupling part, because I think it's going to be useful also for a couple of presentations later. So for the actual simulation just per day, if we take this number as percentage, something that we discover is that, well, if you compare with the simulation just per day, this actual simulation just per day decrease your simulation just per day around 10–50%. And actually we can classify this number in 2 groups. The first one, around 15%, including only the queue time. You know, you run your model is in the queue and well, reduce your simulation just per day around this 50%. And then if we including other interruption, something happened and you stop your experiment, these kind of things, could increase up to this 40–50%. Why we know this? Actually, because this was one of the metrics that we thought at the beginning that people could provide different numbers for the experiment. So explicitly, we asked to the different institutions to say, okay, how you are measuring this particular metric and provide us this kind of result. And we discovered this difference, no, in between the people including only queue time and people including everything. So I find this interesting because this granularity in the metrics I think is important for the discussion. Also, take care about this because actually we did a specific analysis for BSc result and we discovered that this number also changed between different machines, no? And for the coupling cost, also interesting for a presentation from CERFACS before. So if we evaluate one specific experiment, we discovered, you know, we are talking about the same model, and now this model increased the resolution. No, it's a couple model, obviously, and also they increased the parallelization. No, to say, okay, we should maintain more or less the same simulation just per day, and we discovered that for a couple of models, they increased this coupling cost and reduced the simulation just per day, even though this parallelization was increased. In other models, this was not happening. So the problem actually could come from this couple phase. Maybe because the coupling algorithm that we think that actually usually this is not the problem. And maybe because simply this high resolution configuration is not well balanced, no? So at the end, the number of parallel resources that you're using for, I know, the ocean, atmosphere, could be not balanced comparing with the lower resolution. So this also comes with a question. No? This particular institution should waste resources to find the balanced version using the typical trial and error approach, or actually, no, we could provide interesting tools to make this possible in a simple way. So this funny granularity again could be useful. So a conclusion of all this part of the analysis, well, this is not a dissemination process. No, we are not collecting results to put the table and say, okay, this is the number for all the models. We can compare a little bit, but actually we are talking about very powerful tool to analyze our models and try to improve from the computational point of view for future, no, for the future. Well, this comparison I think is very, very powerful because we can compare platforms, different models, find bottleneck, these kind of things, no. And the final one. So this is I think the important for discussion and try to see how to proceed for the future. So I have highlighted from the deliverable some specific bullets, and this is what I'm going to discuss here. The first one, something that I said before, no? During the execution of the experiment, we noticed that actually the single goal for the people, and I understand perfectly this, is finish the experiment. So it's try to collect the CMCC results and nothing else. This means that some institutions try to collect this number, rerunning some specific chunks and try to collect the CPMIP in this specific chunks. This means that, well, sometimes you delay the collection and also, as I say there, no, maybe the machine can change, and at the end you cannot provide these specific results. Also, we noticed that some institution has shown interest from the beginning, but at the end only ENES-RI partner and GFDL, of course, provided the complete metrics. So also this is a question to say, okay, what is happening, these kind of things. So this is the bullet. So now the real answer that I can provide for this is welcome to this dark side of the collection and analysis. So we have some gaps in our number, and they are not going to be updated. And this is what we are now. In any case, I am sleeping very well because we have plenty of information. Most of the results are there for the different models, so there is no problem. However, how to solve this problem for the future? No, we made up to 3 attempts to collect these last values from some specific institution, and what's impossible. One of the main results, for example, they change the machine. No, so in this case, it's impossible to replicate the experiment, and well, it's not something that we can solve. Also, some external partners say, yes, from the beginning, we did some different meetings. Actually, I was teaching to collect some of the metrics, but at the end, they didn't provide the numbers. So, well, also prove that this coordinated experiment could be important. And something which is fun for me, no? We noted that some partners, the collection is trivial. I know from BSc now, from MetOffice, no? It's easy to collect this number, but for others, this is a red cake. So how to solve this, no? So some piece of advice, about this. This coordinated collection proved to be useful for each ENES-RI partner. We have to, we think, facilitate portable and automatic processes to ensure this collection for the different institutions, creating of tools, for example, for decoupling costs, to make easier this collection, a script for automatic collection, these kind of things. And also collect and analyze these CPMIP metrics during a specific stage. So probably the best recommendation is doing deployment, tuning, speed up of our model, for example, in CMCC 7. Probably it's not only for the collection itself, this also could help to increase the throughput of your operational runs in the moment that this comes. And this is actually the work from BSc that we try to do, or we are planning to make this possible, this recommendation that I did before. Include new collection for future projects. For example, we have included in ERI, H2020, in IS-ENES3, is a proposal, but it's there, no? So the idea is we have new collection, we introduce in a coordinated way this kind of activities. Also, we have planned to integrate through AutoSubmit with our workflow manager in BSc to make this collection transparent to the user, provide number automatically, so the scientist can see this number without thinking about this kind of collection. So at the end, the number is there. You can take for a table and nothing else. And also know more about this new load balancing tool for OASIS that Eric will present later. Also, we are doing some work from BSc that we would like to present in the future. And also, we have some discussion to CMCC, because in ENES-RI, we are thinking about how to improve this energy cost, this joules measurement, to try to have something portable and standard for the community. And finally, this recommendation is the same. So find which is the appropriate stage to do this kind of collection. The second one, as I said before, this is not only a dissemination process. So the problem that I noticed from the different institutions, specific details for each component and configuration could facilitate the analysis. No? So if we have the result in a couple model, sometimes it's difficult to understand which is the problem, no? Because maybe you have the ocean, you have the atmosphere, I know, carbon cycle, you could have different components. Let's see if we can improve the granularity and introduce metrics per component, and this could help. Also, this is totally unstable, no? Some HPC expertise could be needed to interpret the result, no? So we have the result, but at the end, we need someone with, to try to evaluate and analyze these kind of results. Also, the limitation of the hardware, because actually you can notice some bottlenecks and say, okay, I have a problem with the ocean in my model, but well, maybe this is coming from the hardware, or actually changing the hardware. This could be in some way solved, no? And also this collection, I know that the people have this feeling, requiring an extra effort, which is not compensated, no? So actually we have to prove that this is not the reality, or at least try to change these kind of things. Which is the dark side of this? Well, for a couple model, no, we can conclude that some issues are actually related with one specific component, and the analysis of the couple model maybe is not useful. So at the end, we have to try to check with a specific, the ocean component, which is the problem. Also, maybe we detect some issue in the model. It's valuable to review this, but well, how we can proceed with this? Maybe we should change something in the algorithmical part. We have to spend time on this, or actually waiting for the new Euro HPC machine, and let's see if this is solve your problem in the scalability part, you know? And the end, this question, no, is actually this effort compensated or not? So some improved recommendation to try to avoid this kind of thoughts. Again, new approaches to include these metrics per component. This could be easy, no? So at the end, actually you can run the AMIP experiment, for example, but also with this, for example, this tool for the coupling load balance analysis, we can take actually some metrics per component, and this should not be a problem. Also, the bigger is the database collection. This is the first one, no, that we do this as European community. The easier will be to follow recommendation for the analysis of your model. So if even though you have not the expertise to do this, we are going to publicate and disseminate some specific paper, and probably in some moment, this kind of recommendation are going to be useful also for your model. Also, something that we are planning for ENES-RI is the integration of this metric in Dwarf. So coming from Escape 2, no? This could be useful because technically we can run this specific Dwarf in different machines, and this could be useful to evaluate, in this case, from the computational point of view, the hardware, no? This particular platform with real model, because this Dwarf is not like a LIMPAC. We are talking about real model for this kind of analysis introducing the CPMIP. So yeah, actually is the last one, no? This integrate the CPMIP in the Dwarf. This is again the work that we are planning from BSc. Also, ESDoc, we update this information per component, the load balance from CERFACS, and also some work that we are doing from BSc. As I said before, AutoSubmit is going to save all this information for the CPMIP for any experiment, but while AutoSubmit is a workflow manager, we can work to replicate this kind of work for AutoSubmit in your machine, in your model, or in the workflow manager that you prefer. And also this dissemination, as I say, for the paper, no? At the end, could be useful for the community in general. And the last one, some inconsistencies, no? For some specific metrics, these actual simulations per day. So we notice, if we didn't ask to say, okay, how you are calculating these actual simulations per day, because in the Balaji paper, technically, it's the time step from the beginning to the end of the experiment. But at the end, some people rerun specific chunks and calculate this Q time. So we discover these differences, these discrepancies in this particular metric because we asked for this, no? In these joules, no, this energy cost, we also noticed that this could be a problem because at the end, all of us, we are believing in the operational people to say, okay, which is the log file from the experiment, which is the energy cost of this specific experiment, no? So this could be a problem, and actually it has happening. In this particular case, we evaluated also with Jean-Claude and Sylvie the core per hours of all the experiment, and we noticed from CMCC, for example, some discrepancy in the numbers. So at the end, we think that actually probably the CMCC numbers are fine as it is, but maybe the way that the approach that we are using to calculate this energy cost could differ, and at the end, in some cases, the numbers are not comparable. So this could be a problem. And also something that we noticed from BSc, post-processing, data management, these kind of things could affect us to the simulation just per day. So if we are calculating this with the simulation chunk, it's going to be impossible to include this kind of part of the workflow, and this actually could be important. I said before that we can fall from 15 to 40, 50% in the simulation just per day. So this, that's again, no? Well, actually, I was talking about everything. 5
minutes including questions.
Okay. So yes, I'm going to finish more or less. So yes, I was talking about this, no? So the problem that we have with the actual simulation just per day, this CMCC issue with the energy cost. Actually, we have another one with MPI before, but we were asking and checking the result. Now it's fine. And well, this about the analysis of the experiment, no? So the solution here standardized for all the institutions to the collection of every metric, I think is going to be useful. Provide new approaches to collect the metrics, which could be comparable across platform. As for example, we have some activity collaboration with CMCC to try to solve this for the energy cost. And integrate the collection through the workflow manager for long period of simulation. So at BSc, for example, we try to, if 200 of years of the CMCC experiment, 200 to do the collection and the analysis. So this is more or less the idea, no? As I say here. And well, so nothing else. So I hope to now or later to have some discussion of this or contact, and let's see how we can improve for future collection and try to see how we can ensure that this could be trivial for everyone, for all the institutions, for the future collection, and at the end provide analysis and result that is the most important. So nothing about this one. So thank you.
Okay, thank you, Mario. We have one question in the Google Doc. Suvi, how do you calculate energy estimate? Is it estimate from what? From processors use time hours or some other way? And is what kind of compute processor use part of CMIP?
Well, actually, it's a good question, I said before, because technically should come everyone from the different institutions to answer this question. So we have not an standard, and this particular energy cost for most of the people is coming from the specific machine. So, for example, -4, you can collect this particular value directly from the log file. So in the log file, you are running with a specific number of processes. So at the end, this is a particular core hours, and we can use this to automatically calculate this energy cost. No? So you are using 1,000 cores during 1 hour. So this is the energy cost for your experiment. Probably for most of the institutions it's like that, but also I know that some people say, okay, which is the energy cost for this experiment? Is this one? So I believe this is the way that also we are taking this particular number. So I find interesting to try to evaluate, to understand how this is possible, how this can be collected, and try to provide a standard for the future.
Okay, thank you. Other questions? Maybe directly here? No? Okay, so just one comment. I think that sorry.
Excuse me.
Yeah.
Just one question. Can you elaborate a little bit about the energy consumption?
Can you speak in the microphone?
Sorry. Can you elaborate a little bit
Turn it on.
This is on.
Okay.
Can you elaborate a little bit about the energy consumption measurement, the portable way CMCC is working on?
Good question, because I see your I see what you are asking. I think this is going to be difficult. So the idea, I know that actually Italo could say more about this, because they have an approach, and we are going to discuss this afternoon about this. Well, I think that we are thinking about some specific software, no, or profiling, and the idea is try to install these kind of tools in the different machines and use it for this kind of energy measurement. As I think Italo want to say something, and also if you want to join us to do this in the future, you are welcome.
Yeah.
From Atos.
Thank you very much.
yes, sir. The problem is not so easy. The portability is not. It's difficult to guarantee the portability for heterogeneous architecture. So we leverage on the internal registers. Like, for example, for the Intel, use the MSR register. NVIDIA use the NVML register, and so on. So the idea is to create a layer in order to be compliant with the architecture and the CPU and GPUs that has the internal counters for the power consumption.
Okay, thank you. We have to go on. Just one comment. I think one problem came from the fact that the definition of the metrics themselves were not so precise. For example, you know, on the data transfer, on the data produced, what does it mean exactly? And the other thing was that it was asked during the process. I think we will be in a better shape next time because we should ask for those metrics before the exercise. So, okay, so now we can switch to Italo Epicoco from CMCC, who will discuss performance optimization in NEMO Ocean model. So I will tell you 5 minutes before the end, including questions.
Yeah, thank you. Okay, so good morning, everybody. It's nice to see you again in person. And so my name is Italo Epicoco. I'm from CMCC in Italy. And today I will present you the activity we have performed around the NEMO optimization in HPC. So today I'm just the interface behind this work and behind all of the activity that we described. There is a wide community of HPC experts. Here in the slide, you can see the logo of the main institutions involved in the NEMO optimizations. And I have also reported here the main funding project where all of the activities took place. So IS-ENES, IMMERSE, ESCAPE, and EASY-WAYS are the main project where all the activity concerning the NEMO optimization have been found. So in my presentation, I'm just give you an overview, a list of all of these optimization, but I will be more than happy to delve into details with anyone is interested. So I just give you the list at the high level. And the activity just touched many or all of the problem regarding the HPC, starting from the optimization to exploitation of the single node performance means that we have to deal not only how to speed up in parallel models, but also we have to deal how to better exploit the resources in a single node, like, for example, the exploitation of the cache memory or to enhance the arithmetic intensity and so on. Then other activity concern the optimization or the reduction of the communication overhead for the parallel execution, or enhancing the macro task parallelization, enhancing the workload for the multi-grid refinement, and the use, of course, of dealing with the I/O operations. And at the end, I will just give you a brief introduction on how we have tackled the problem of porting the NEMO towards the GPU architectures. So a couple of words about the NEMO consortium. So the NEMO model is maintained by a consortium. The consortium was formally built in 2008. And the members of the consortium are listed here. That's CNRS in France, Mercator Ocean, Met Office in UK, NOC in UK, and CMCC. So the NEMO consortium is organized into several bodies. The main one is the NEMO system team, which is responsible for development and distribution of the NEMO reference code. At the beginning of every year, a list of actions are established by the NEMO system team for developing And these actions must be compliant with the NEMO strategies. This NEMO strategies is built by another body named NEMO Developers Committee that also have to take into account all the discussion around and make it inside the NEMO working groups. The member of the NEMO working groups is not tailored only on the consortium institution, but is a wider community. And I listed in the first slide all the members that participate to the NEMO working groups, specifically for the HPC working group, which I led. And at the end, we have also other bodies for, let me say, for the control, like the Scientific Advisory Committee and the Steering Committee. So, starting with the activity for the optimization, the first I will list is listed here in this slide is the loop fusion technique. This is an optimization technique that aim at enhance the exploitation of the cache memory. So the idea is that when we have two different loops, every point in the domain is swept once, but in the second loop we have again to sweep the same point, but now the point is not anymore in the cache miss, so we have cache misses. The idea of fusing the loop enhance the exploitation of this cache memory, since the idea again is to perform all of the operation on one point before moving to the near points. And this optimization, these techniques is quite trivial when the loops perform on the same interval. These techniques is not does not lead to benefits when the loop has several dependencies. So the other drawback of these techniques is that it's not maintainable. I mean, when the model evolves, and we know that the developers of the NEMO are not all HPC experts, so it's not so easy to apply these techniques also by people that are not HPC experts. So the idea is to apply these techniques in automatic ways, for example, by an automatic transformation of the code that is, for example, inside the DSL or domain-specific language. I will show you on the last slide some configuration about that. A complementary approach to the loop fusion is the tiling. Again, the tiling has the same idea, the same goal. The idea is to partition the local domain into smallest tiles that can fit on cache memory. So the idea is to perform all of the time step, one single iteration of the time step inside one single small tile before moving to the near tile. And right now, the tiling approach has been included in the last version of NEMO, NEMO 4.2, but is implemented only on 2D. And so the tiling optimization is ongoing, is still ongoing, is not still optimal. This is one of the main drawbacks for the tiling approach, which when dealing with the halo calculation, because we have some redundant operations for dealing with halo. And the other problem right now is the tiling calculation are not independent. So it's not possible to compute the operation independently one time from the other tile, and this prevents to further insert the OpenMP parallelization of the tile right now. So the optimization, the activity is still ongoing, but for the improvement we measured so far, we got an improvement on 1.4x with regard to the previous version of NEMO, applying the tiling loop fusion. And this the tiling improvement strongly depends by the platform, so also regarding to the use and the dimension of the size of the cache memory, but also is strictly depending on by the configuration used in NEMO. Some of the improvements that will lead to much more improvement for tiling is to extend the tiling also towards the vertical direction, so to have tiling in 3D. Here are reported much more encouraging results when you have to look at the red line that just proved that with tiling along the vertical direction, we can also reduce the timing at 60%. And the other aspect that impact on the tiling is also the vectorization. This is one of the last experiments we had. We have measured it. An example is for one single routines in the advection scheme, the Muscle scheme. The use of the non-intrinsic sign functions limited the vectorization, but when we enable the vectorization, we experienced an improvement of the performance up to the 70% compared to the 25% of the case without vectorization. This work has been led by Met Office. Again, for the better exploitation of the single node resources, I like also to mention the mixer precision. Yesterday, we followed the presentation by Samuel regarding the single precision at IFS. And also in NEMO, the BSc group is working on support and to introduce support for not a single precision, but a mixed precision. So the advantage is to use a lower precision for representing the floating point numbers is quite evident. So with the low precision, we could reduce the memory footprint, we could enhance the arithmetic intensity, we considerably could improve the parallel scalability. So all of the advantages have been also explained yesterday by Samuel. One of the main concerns about this is, again, the model accuracy. But with this approach, with the mixed precision, and just with an appropriate tuning of variable that must be downgraded at single precision and other variable that must be kept in double precision, we could preserve the model and the result accuracy. The automatic emulator is able to, developed by BSc, is able to identify a set of variables that can be safely used in single precision without impacting on the model accuracy. And in this slide, you can see on the left side the difference, the errors between the mixed precision output against the full double precision execution of the model. And as you can see, both lines, the blue one and the green one, overlap. This means that there are no evident differences between both approaches. And this has been evaluated also for multi-year simulation. And on the right side, you can see the improvement of the parallel scalability using the mixed precision support. Yes, this slide is just to mention that a fully single precision version of NEMO has been used by the SEMWF for coupling with the atmosphere, for running for the forecast and seasonal studies. And here the plot report the improvement of about 1.6 x 1.6. Okay. Okay. So just going faster, the other optimization I'd like to mention is the reduction of the overhead for MPI communication. We use the neighborhood collective that has been introduced in the MPI standard version 3. So we substituted the point-to-point. Okay. 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 Yes, I will conclude in 5 minutes. This is the message. Okay, thank you. And okay, so we have introduced and we substituted the point-to-point communication with this collective neighborhood because the pattern, the communication pattern, allows us to use this kind of communication. We have reduced it we dropped the communication cost of 30%. The other activity is concerning the improving the parallelization of the NEMO, just the coupling or the biogeochemistry module, and using an approach like the standard one with the couple model, so it's possible to execute in parallel the ocean and dynamics part, the physics part, concurrently with the biogeochemistry model. And the coupler is used is OASIS. The other the other aspect concerning also the I/O operation, NEMO leverage on the external tool named XIOS in order to asynchronously perform all the I/O operations. So XIOS is a powerful tool for handling efficiently the I/O. And we, in the last year, we have extended the use of XIOS inside NEMO also for reading initial condition and writing restart files also for the CIS-Cube component. And the other still we have optimized so the load balancing inside NEMO regarding the management of the nested multigrid. This component is named Agrif, and Agrif had, before our optimization, Agrif performed worse because we had a lot of unbalancing. After this optimization, we, so the ENES-RI worked on that, achieved a speed up of 1.4x on average, just modifying the policy on how to balance the load when multiple nested grid are evaluated. And last, I have the last 3 slides just to mention the work towards the migration to the GPU-based architecture. One of the first experience has been done by the SC group, just offloading the diagnostics. In their approach, they used the CUDA in order to execute the diagnostic concurrently with the other part of the NEMO model and reaching a really promising result. Again, this approach is not so maintainable for the people that are not HPC experts. So the main, the most promising activity that will conclude my presentation is about the use of DSL. The DSL I am referring is named Cyclone. And Cyclone has been developed. One of the branch of Cyclone is devoted only specifically for NEMO. As you know, the domain-specific language leverage on the idea to define a new language close to the domain. In this case, Cyclone used the code structure inside NEMO as the language. So Cyclone is able to understand the code structure of NEMO to perform automatically the transformation, code-to-code transformation in order to apply in this case, and to instrument, to apply automatically to recognize the parallelism in order to insert into the code the OpenACC directive, or in last version also the OpenMP directive automatically. In the slide, I have reported some experience from the STFC group in UK, which have used Cyclone to, let me say, compile NEMO to be run on a single GPU. On the left side of the slide, you can see the execution of a low-resolution ORCA at 1 degree that fit exactly on one single GPU. So they got an improvement of 3.5x on executing the whole NEMO code into one single GPU. And so behind there is the case with also with the ICE model, C-ICE model. But they have also run a version, a configuration at a high resolution, 112 degree, the Orca 12, with multiple GPUs, so with hybrid approach MPI plus GPU. And they got really, really encouraging results in order to port NEMO toward GPU. Again, this is performed with automatic transformation using Cyclone that, starting from the current Fortran code of NEMO, is able to transform and to produce a version of NEMO suitable for running on GPU.
Sorry, Italo.
And that's all.
4 minutes now, including questions.
And that's all. I concluded here. Thank you.
Thank you, Italo, for the presentation. So we have some questions. The first one from someone online. Is loop fusion not normally part of the compiler optimization?
Yeah, yes, the loop fusion, or let me say the trivial operation is included in the compiler optimization, but is not enough. Most of the time, the compiler is not able to fuse much more complex loops, or is not able to fuse loops that include some dependencies in the iteration dependencies. So again, the loop fusion leads to an improvement, but is not applicable manually. I mean, we need an approach like Cyclone, and we could implement an optimization into a transformation into Cyclone in order to automatically transform and fuse the loop starting from the legacy code.
We have now from Uwe, so you can, if you want.
Yes, a simple question. I was wondering if the reading of initial conditions with 6iOS was part of NEMO 4.2. Sophie gave already an answer in the
but I'm not sure of the,
yeah,
the answer.
but you wanted to have
so maybe, maybe Jan, you can say something about that?
Yeah.
Or Sébastien, yeah?
Sébastien.
Yes. I mean,
yes, it's
reading the restart. It's with XiOS. That's your question.
Yeah.
No?
Yes.
Yeah.
Yes, and initial conditions as well.
No.
Initial files not.
No.
Yes.
Yes.
But we agree there is supposed to be a support about this, right? And it's ongoing, or it's starting, or it should start soon?
It should start soon. Tomorrow, for sure.
Okay, you start at the break, right?
Yes.
Great. Thank you.
And we have more online. For single precision, NEMO, beyond identifying variables that can be stored and computed in single precision, were there any algorithmic changes applied? Some examples: scaling, reordering, error compensation. So maybe from BSc I can ask.
Yes, it probably is better if you directly answer
is there.
Yeah.
So in our case, please consider that the first step is try to identify this variable, and our plan is that maybe if 80%, in the future 90% could be in single precision. So at the end, this is the most important part in our work just right now. As second step, after this, and try to prove that actually we are improving the performance that just right now is there. If other approaches, for example, this error compensation, could be done for this algorithmical part that could be improved. I don't know if Sam want to say something from ECNWF or not. Okay.
Okay, so I think we can go on with the talk from Eric Maisonnave from CERFACS on the new load balancing tool in Oasis Stream CT 5.0 that was mentioned a few times by Mario. That should help to get those CMCC metrics that we discussed earlier this morning.
Yeah, thank you, Sophie. So yeah, I will talk about the new load balancing tool in Oasis, in the new version of Oasis. So the first part of my talk will be a little bit low level, and then I will try to give my user point of view about the new functionality of Oasis, or other functionality than the load balancing tool. So all the functionality are detailed in the user guide that is available on the Oasis website. So the Oasis is available with Git, and in addition to the code, there is a Spock that also available to better understand how to use Oasis, because it's important also to give services around in addition to the tool. So I list here some functionality, not all the functionality that are available in the new version, and I will focus on first on the load balancing tool. So this new, there were a load balancing tool in the previous version of Oasis, but this new tool is give more detail about the how the coupling is really it gives more detail about the coupling practically during the simulation. So it's an internal tool. It's not something revolution. It's not a revolution. It's something that is already available with external tools, like for example Paraver that is developed here at BSc. You can visualize the different different function, and in particular the function in link with the coupling, the Oasis function in your model. But here with this tool, you don't need to instrument your model with a new library. It's coming with the Oasis library, and this tool makes possible the measurement and the visualization of every event, every routine in link with the coupling, and make possible to evaluate the coupling cost that Mario defined in his previous talk, and this on every coupled process. So basically, this is the kind of graphic you can visualize with this tool. So during the simulation, in the timeline, you have a timeline for every MPI processes of your involved in the coupling. So here I am. You can see two model exchanging coupling fields, two coupling fields, the SST and the ice cover, for example. And with this visualization tool, you can see when the sending of the SST is starting on every MPI process, how much it lasts, and this for each coupling field. But you can also have the same information, not on a coupling field basis, but on the kind of coupled operation you are processing. For example, the sending in red, which is basically a MPI send, a receiving, the MPI receive, and the phase where Oasis is interpolating the coupling field when the grids of the two models are different. So this is the kind of visualization you can make well, the Oasis during at the end of the Oasis at the end of the coupled simulation, Oasis is writing the information about the information I show here is written on an NetCDF file. We choose the NetCDF format because the NetCDF format is something well known in the community, so it's easy to visualize NetCDF format files. And then you can visualize this information with the visualization tool you want. So for example, here at BSc you have a different visualization tool. Here we choose the Matplotlib. And here the example I show here is the coupled system made with the ICON atmospheric model and the NEMO ocean model. So the MPI rank of the ICON model are located below and above the NEMO MPI processes. This is quite a short simulation, and well, basically what you see here. So I show one color for each coupling field, and you see that the SST exchange takes a lot of time. At the beginning of the simulation, well, it's during the initialization phase. So if you just compare the color area, which represents the coupling, and the white area, which represents the time you spend in the model for internal computation of the model, it looks like we spend a lot of time doing coupling, but in reality, the main big box at the beginning, the gray box at the beginning, is a waiting time. ICON is waiting an information that NEMO is not providing. It takes time to provide this information because we are simply in an XIOS initialization phase. So it's not a fault of OASIS; it's a fault of the culprit is XIOS here, Jan. What we can identify as a coupling cost, in reality, it's the time spent by XIOS. Not really XIOS. It's probably the writing of the first NetCDF file by XIOS at the beginning of the simulation, and it's probably longer in this machine. So this is the kind of information you can deduce from this graphic. With this visualization tool, we chose it's possible to do zoom. So it's very useful to go into more details. So if I do a zoom on the red rectangle, I can have an information about not the initialization phase, but information during the computations. And you see here, so I plot here not one color per coupling field, but one color for each OASIS operation. So for example, in red, it's when I receive a field. In blue, when I'm waiting a field. Green, it's when OASIS is doing the interpolation, and so on. And in white, it's the model computation. So you see here that the irregular model time step in ICON, as a consequence, sometimes ICON is waiting an information coming from NEMO, and sometimes it's the opposite. So in this configuration that you can, I think, also see with IFS NEMO, the irregularity of the time step makes that the two model are waiting the information from the other model, and it's extremely difficult to find the best load balancing between the two model. It's difficult to find the best number of processes to attribute to each model to have the best load in balance. So if I do a zoom on one coupling sequence, just one coupling sequence in NEMO, you can even see that it's difficult to find the good load imbalance, the internal load imbalance of the model is delaying a little bit the phase of coupling. So you see there are some. We spend some time between the moment when the first process is ready to send the coupling field and the moment when the last process is ready to send the coupling field. And this synchronization is adding a coupling cost, but it's not, the coupling cost is not a consequence of longer interpolation. It's really the consequence of this model jitter. So the main information is that our tool can help the user to address the load balancing issue sometimes when it's possible, and possibly reduce the coupling cost. But the 2D interpolation and the exchange or the exchanges during the coupling are a problem of secondary importance compared to the load imbalance between the component or internal load imbalance in the model. More information about the different new functionality in OASIS. So in this new release, as I say, Sophia has developed short private online courses that are available online. Because the community of OASIS user is still a growing community. So we have to provide information to this community. And this community is also an active community. The developers are reporting bugs. Sometimes they are correcting bugs. And they also, more importantly, they also develop interfaces in the model to be able to use OASIS for communicating the boundary conditions. So many of our users are NEMO users or WARF users, but not only, but a big number of users are from this community. Mainly because the interfaces are quite modular. They have been developed to be able to plug NEMO and WARF to many other models. So it creates a kind of de facto standard of coupling for this model, and it speeds up the implementation when a user wants to plug a model to NEMO or WARF. It's easier to plug another model with OASIS than with another coupler because the interface is already there. So it speeds up the implementation of the coupled system. So how to keep this link with the community? I think Fortran is a key for us because most of our community at the moment know how to use Fortran, so they know how, they can even have a look to OASIS if there is a problem into OASIS, which means that it is really an open source code for that reason. But not only. Fortran, it's also important to have a compatibility between the model and the coupler, even though in this new release, Python C and C++ interface has been developed. API have been developed in OASIS, so now it's possible to plug a model written in Python, C, or C++ directly with the OASIS library. I don't know if the next step would be to redevelop OASIS in C, C++, because you know that the new couplers are developed in this with this language, like XIOS or YAC. Well, for me, it's unclear if we have to keep Fortran or if we have to change to another language. The Fortran community is still there. There are a lot of models developed in Fortran, and probably it would be the case for the next for the years to come. So it's unclear if we have to change the language. Because it's also important to have a language that everybody is able to understand, because the coupler is not only a technical software. There are science inside this software, and it could be interesting to involve the community in the coupler development. Here in an example, we have developed a very domain-specific interpolation just for the river runoff, thanks to an idea of Aurore Voldoir and Météo France. We always have a problem of coastline mismatch between atmosphere and ocean model, because atmosphere and ocean are discretized on different grids most of the time. And there is no intersection between the meshes of the atmosphere or the land model and the ocean model. So for that reason, it's difficult to use the interpolations that are available in the community or in other communities. So we develop a specific interpolation that totally changes the result, as you can see in the two graphics. For the same input, the same runoff provided by a land model, we have totally different result with the nearest neighbor interpolation at the left, and the new interpolation at the right. So we have much more precision on the river mouth grid point of the ocean. And needless to say that the simulation, the two simulation, the ocean simulation with the two interpolation are totally different also. With this new OASIS version, benchmarking of different interpolation library has been processed, and a unified environment to generate the weight, the interpolation weight, is now available. So you can generate weight with script, ESMF, XIOS, and it's possible to reuse this weight with OASIS, and we did that because maybe the script interpolation that is available in OASIS, it's probably not it's a little bit outdated, and it's interesting to be able to use interpolation from other COP interpolation library. And more generally speaking, it's the problem of compatibility of OASIS with exascale couplers. So the question behind are we able to have a coupler that is that could still have good computing performance on many core model or many core hardware or GPU? Yes or no? It depends on how many core are really involved in the coupling. It's still unclear for us. For example, in the Chinese machine, I saw that not all there are many cores, but not all the cores are involved in the coupling. So maybe it's not important to have a library that is able to couple all the core of these machines. Another pending problem is the problem of the non-Eulerian grid or dynamical grid that are changing during the simulation. I don't know if it is really necessary to have a coupler that is able to couple this kind of grid, because as we see in recent development, for example, in the new next SIM model, it's difficult, for example, to have good performance on this big machine with Lagrangian model. So maybe it's not that important to be able to couple, to have dynamical regridding and coupling of dynamical regridding in the future. Yeah, this is my conclusion, my two conclusions. If you think that a coupler is just a runtime library that collect and provide boundary condition at model interface, so if you think that a coupler, if your point of view is a coupler it's a tool, probably that the OASIS tool is a little bit outdated at the moment. Now we maybe the community should think about moving to another to a more modern coupler. Or maybe with a coupler that is written on a more modern language. But if you think that a coupler is, if you see the coupling as the community activity more than just a coupler, you see that this activity is also evolving. And for example, there are very new problems that are now have to be addressed by the community. I listed some of this new interesting problem that people are investigating, and probably there is no coupler that is able to address all the problems. So maybe OASIS is one of the tools that could be able to, at least at the beginning, start addressing those problems. So it's an interesting tool for the community, useful, quite easy to use for the community, and to be able to start investigating the physics of the interface. And that's it. Thank you very much.
Okay, thank you, Eric. We do not have any questions in the Google Doc. Do we have any questions in the audience? Yes, Willem?
Oh, me? Okay. Eric, from FESM team, thank you for maintaining OASIS and especially doing it in... Sophia. Sorry, Sophia. And for doing it in Fortran. And a question regarding runoff. So it's available only in the new version, and it's conservative remapping. Yeah? And I asked myself, so in a CMIP contribution, which has been committed, so this feature was not available yet. And how did people deal with these problems? So they did something on side of OASIS, or what? I mean, how did they couple the runoff? That's the first question. And another question is like rather maybe a feature request. What I recognized recently is that when we couple from model A to model B, so we have like ice concentration, and for instance, yeah, which is like not given, it varies from 0 to 1, and we have flux which goes into the ice. Yeah? And when coupled to model B on a different mesh, we conserve the remap ice concentration, and we conserve the remap flux into the ice. But what we need to conserve like flux multiplied with ice concentration, which was computed on a model A. And I also recognize that it leads to some residual, actually, in the total flux between components. And whether it's like a feature request if you have some plans to implement.
So regarding the flux question, I guess it depends on how you implement the coupling, and how you use OASIS conservative remapping. So we can discuss that offline, because this would be a problem, but a long discussion. But yeah, I understand what you're talking about, and we've checked that this is done correctly in our model. So we should discuss that offline on how we do that.
We also do it internally, a lot of tricks, but yeah. It would be good if just OASIS takes care of this. Yeah? And it's regarding about the first one. What about runoff? All these models in CMIP who were using Oasis, yeah, they also all have river runoff component in there, and it shall be conserved. And so they had another coupler for runoff. I don't know. I'm just not aware. And they used Oasis for the other fluxes.
No. I know that we've discussed that with few groups, and they were aware of this problem, basically, that you have to be conservative, of course. But in this case, the question is that you have to make sure that all the runoff that comes from the source grid is going somewhere. And we were not doing this properly in CNRM CM6, and it changes the results. So yeah, so it is a problem with some of a part of our results in CMIP 6. But I know that we've discussed that at the coupling workshop. The latest coupling workshop, and I know that it's not a problem for most models because most people were doing that correctly. Okay. So we would have to check. It's a problem for our model. It was.
Thank you.
It's always conservative. The problem is where you put the
where you put
exactly.
It, but conservative is the first order of what needs to be preserved and where you put it.
No, but it changes our AMOC, for example. Yeah. So it has a strong impact. So we should go for the break now. Let's reconvene. Let's 11:18, so to be on time for Renard Boudé's talk. Thank you.